Salam sejahtera. My name is Siti Nur Hashimah binti Muhammad Razali and my matrix number is AE190046. I'm from group 4. So today our group will briefly explain our problem based on learning PBL2 on topic 4, digital modulation and transmission. Before I start my presentation, let me introduce my group members first. Our group consists of 5 members including me, which Muhammad Afiq bin Ahad Rul Nizam, Muhammad Amir Ridwan bin Muhammad Ghazali, Amar Sofi bin Zamzuri Arifin, and Putri Balkis binti Amran. On this PBL2, we require depth knowledge of pulse code modulation technique to analyze the complex problem of analog to digital conversion and digital signal transmission. We are also given different scenarios to analyze and discuss the resultant recovered modulating signal. Okay, so first, let me explain what is pulse code modulation or known as PCM. PCM is a method for converting an analog signal to a digital signal in the telephone network or ports. And an 8 kilohertz sampling rate is used to sample the analog signal first. Each sample is then quantized into one of 256 levels and digitally encoded into 8-bit words. Okay, according to the PBL2 trigger statements, pulse code modulator circuit digitize the given analog signal, codes it and samples it, and then transmit it in an analog form. This whole process is repeated in a reverse pattern to obtain the original signal. However, the encoding and decoding process must meet certain crucial requirements, including sampling frequency, quantization in interval voltage range, and allowable amplitude modulating in certain range.
Okay, for the fila table, our group did for the each part, which is part A, part B, part C, and part D. Okay, so this is for the part A. First of all, the facts is the sampling for the MT is the minimum required, and the bits encoded PCM data is given. And for the ideas, first idea is the higher the resolution, the higher the maximum quantization error. And the second is the amplitude of sampling signal after the transmission should be lower than the amplitude before the sampling signal. And the third idea for part A is the higher the n bits encoded PCM data, the higher the encoded signal. Okay, for the learning outcome, which is issues, okay, what is the waveform of the sampling signal? And the second is how the n bits encoded PCM data influence the encoded signal. And the third is what happened to the waveform after the transmission process. And the action for part A, our group do further research for gathering the information from website and books. And we also do the simulation to observe the result. Okay, so for part B is actually the same as part A, but the difference is the sampling is more than required. Okay, then for the part C, okay, the part C is the sampling required is lower than minimum, and for the ideas is the amplitude of the sampling signal of the transmission should be lower than the amplitude before the transmission, and also the amplitude should be decreasing after the transmission process. And also for the learning outcomes, what is the waveform of the sampling signal and what is the pulse waveform for the both for bit encoded pulse code modulation, and also what is the waveform of the modulating signal. And our action is also to simulate the circuit and observe the waveform results same as the others. And lastly, for the part D, the fact says the value of the amplitude is given, and for the part D for both question, we find out the same ideas, okay, which is find the maximum quantization error, and then we need to observe the amplitude of the sampling signal and compare the waveform of the encoded signal, and lastly we recorded the amplitude of the waveform of the modulating signal to find the solution. And for the learning outcomes, what is the waveform of the sampling signal before and after the transmission? What is the difference of the encoded signal for both bits? And what is the result shown at the display of encoded pulse code modulation? And lastly, what is the waveform of the modulating signal after the transmission process? And for the action, we calculate the value of the maximum quantization error by using the formula and conduct the simulation. So that's all from me. Thank you.
Assalamualaikum, my name is Muhammad Amir Ridwan bin Muhammad Ghazali, matric number AE10036. So for this part, I'm going to explain the flowchart of our brainstorming process. So the process began with the discussion by understanding the PBL2 given tasks, and then all the group members search for reference and sources on the internet, and then we collect all the reference and the sources, and then it was being compared to find the best possible idea to solve the problem in PBL2. And then all the group members solved the problem using MATLAB, and the result was discussed, and then all the group members were agreed on the proposed solution. Now for the result and discussion part, I'm going to present the result for part A, which is the sampling for message signal is the minimum required according to Nyquist theorem. So basically there are two scenarios, which is the sampling frequency is same for both scenario, and the only difference is number of bits encoded PCM data. So for the scenario 1, we have the 4 bits, and then the number of quantization calculated is 16, and then the resolution is 0.667 volt, and then for the maximum quantization error we got 0.333 volt. And then for the scenario 2, which is 8 bits, we calculated the number of quantization is 256, and then the resolution is 0.03922 volt, and the maximum quantization error is 0.0196. Next, this is the waveform of sampling signal on sample and hold and filter. So basically on left side we can see that the orange waveform graph shows that the sampling signal after the sample and hold process, and then being compared to the right side, you can see that the orange waveform graph shows the waveform of sampling signal before filter process. And then this is the comparison of encoded signal for 4 bits and 8 bits. So basically for 4 bits, the orange waveform is actually the encoded signal, and then the same to the right side, which is the waveform of encoded signal for 8 bit, which is represented by the orange color waveform. And from the observation, we can see that the encoded signal for 8 bits is higher compared to encoded signal of 4 bits. And then the comparison of pulse code modulation for 4 bits and 8 bits, as you can see from the simulation, we get 4 sample of time for 4 bit encoded pulse code, and we got 8 pulse waveform for 8 bit encoded pulse code modulation. So now we need to compare the analog signal before and after transmission for 4 bits and 8 bits. So on the left side we can see that the blue waveform is actually the recovered message signal, and we can see that the amplitude decreases to 3.143 volt. And then on the right side, which is the 8 bits, the analog signal is represented by the blue waveform, which is the recovered message signal, and the amplitude decreases to 3.477 volt. Now for the part B, the sampling for message signal is now more than required according to Nyquist. So the scenario 3 and 4, the sampling frequency is bigger than 2 time message signal frequency, also the same as scenario 4, and the only difference is the number of bits encoded PCM data. So now we should see the comparison of encoded signal for 4 bits and 8 bits. As you can see, the orange waveform indicate the encoded signal, and now if we observe the encoded signal for 4 bits, we can see that the quantization level is more than the previous cases in part A, which is lower. And now we should see the analog signal before and after transmission for 4 bits and 8 bits. So basically for 4 bits, the blue waveform is indicate the decoupled message signal, and same goes to the right side, which is the waveform for 8 bits. The blue waveforms shows the decoupled message signal, and for the 4 bits, we can see that the amplitude for recovered message signal decreases to 3.150 volt, and for the 8 bits, the amplitude also decreases to 3.370 volt. So if we compare to the part A, the amplitude is actually higher than part A.
My name is Amar Sofi Bezamzuri Arifin, matrix number AE190061, and I'll be presenting for the result of part C. So for the part C, we choose the FM value, which is 50 Hertz. And for the result, we get like this, which is for the sample and whole one and filter. The left side is the sample and whole, while the right side figure is a filter figure. So for the amplitude before filter process is lower compared to the sampling signal on sample and whole. While for the encoder and 4 bits PCM display, we get that the encoded signal is represented as orange waveform, while on the right figure, there are we choose 3 sample of simulation time taken for the PCM display. And moving on to the analog signal of 4 bits transmission, as you can see, the output signal is lower compared to the input signal. So for the modulating signal, which is the input, the amplitude is 5 volt, while the output signal, which is the recovered signal, is 3.181 volt. Moving on to part D. So for the first one, which is we set the VM to 15 volt for the sample and whole and filter figure. We can see that the amplitude before filter process, which is the orange waveform, is lower compared to the sampling signal on sample and whole one, which is the blue waveform. While for the encoder for 4 bits and 8 bits comparison, we can see that encoded signal for 8 bits is higher than 4 bits, which is the orange signal, orange waveform. And moving on to the PCM display comparison for 4 bits and 8 bits, we can see that pulse code modulation of 8 bits contain 8 components compared to the 4 bits, which only contains of 4 components. And moving on to the analog signal for 4 bits and 8 bits comparison, we can see that both of the output signal is lower compared to the input signal, which is for the input, each of figure is 15 volt and for the output for 4 bits is lower, which is 9.544 volt, and the output signal for 8 bits is 10.53 volt. So moving on to the second Roman, which is VM equals to 0.5 volt. For the sample and whole and filter, also the amplitude before filter process is lower compared to the sampling signal on sample and hold 1, while for the encoder for 4 bits and 8 bits comparison, you can see that the encoded signal for 8 bits is higher compared to the 4 bits encoded signal. And moving on to the PCM display for 4 bits and 8 bits comparison, you can see that 8 bits PCM display shows of 8 components, while 4 bits only shows the 4 components. While and moving on to the analog signal between 4 bits and 8 bits, you can see that the output signal for both is lower compared to the input signal, which the output signal is 0.318 volt and 0.351 volt respectively. And for the suggestion to make sure the resultant recovered signal is same as the modulating signal, we choose to add a gain block function in the system with the value of 1.4 volt. And the right side, we can see the result or the comparison between before we adding gain and after we adding gain, which we can see that the output signal, which is the blue waveform, is increasing quite similar to the input given, which is on the above figure. We can see that the output is 3.51, and for the with the addition of gain, we can see that the amplitude increased up to 4.9, which is equivalent to 5 volt. And so for the discussion, from the simulation and result, part B produced a better signal output compared to the part A. This result obtained by applying the Nyquist theorem, which the value of sampling for part B is much higher, which is 1000 hertz compared to the part A, which is only used 200 hertz. However, due to the value of sampling rate is lower than Nyquist theorem statement, so for the part C, we only use 50 hertz, which is for the sampling rate is equivalent to 100 hertz, and it causes aliasing to happen and cannot be digitalized accordingly. So for the number of quantization, the higher number of quantization will lessen the resolution value and indirectly decreasing the value of maximum quantization error. So as a result, 8 bits of data system will produce a better output compared to 4 bits of data system. This is because the number of quantization for 8 bits is 256, while for the 4 bits is only 16. And last but not least, for the modulating signal, so 0.5 volt modulating signal produce a lower quantization error compared to the 15 volt modulating signal. So hence the output for 0.5 volt modulating signal is better with reference to its amplitude.
Assalamualaikum, I am Muhammad Afiq bin Ahlul Nisam and I will conclude our project. So what is PCM? PCM is pulse code modulation and it's defined method for converting an analog signal to a digital signal in our telephone network. So it will digitalize the given signal, codes it, samples it and transmit it in an analog form, which the whole process is repeated in a reverse pattern to obtain the original signal. So from the PBL project, a Nyquist theorem was used in order to convert analog waveform into digital signal. A change in a VM value made a huge difference on the result. Nyquist theorem require higher value of sampling rate in order to digitalize the signal accordingly. So a manual calculation was done to prove that the number of bits in PCM process is important in quantization process. And lastly, the significant value of amplitude also play a huge role to determine the voltage range from the result. higher value in amplitude increase the resolution and the maximum quantization error. That's all from our group. Thank you.